Hi there. So for this section, we're going to talk about properties of rational functions. And what a rational function is it's a regular function, but it's basically a polynomial divided by a polynomial. And there are a lot of different properties that we're going to look at in this section. We're going to start out with when there are holes actually in the graph itself. And that happens when you factor one of the two polynomials and one of the terms actually reduce out. So in this example here, you can see x still cannot equal -4, but you can see they reduce out. And it becomes this function right here, just the x plus 3, which is basically a straight line with a slope of 1 and a y-intercept of 3. However, x still can't equal -4. So when you plug in -4 here, you get y equals -1. So at this point, when you draw the graph, although it's a straight line, right there we have a hole. Once again, the holes only occur when something reduces out. When something doesn't reduce out, then we run into what are called asymptotes. That's this funky word right here. We're going to start with vertical asymptotes. Vertical, of course, means up and down. And that is basically when we are dividing by a 0. The only exception to that is when it reduces out and we have a hole like we have up here. So vertical asymptotes, again, occur when we have a 0 in the denominator. Now, a horizontal asymptote is a little bit more tricky. Horizontal asymptote, of course, horizontal is this way. Although we can never cross a vertical asymptote, ever, under any circumstances, horizontal asymptotes we do sometimes. They cross quite easily. And that happens when we're going out to the extremes, as x is going to infinity. With the vertical asymptotes, it was when y is going off to infinity, that's f of x, versus x going off to infinity, like we have here. Positive and negative infinity. So what's going to happen is we're going to run into several scenarios, and I actually want to go through this bottom part first. When the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is the x-axis. It's y equals 0. When the degree of the numerator is the same, the horizontal asymptote is going to be the ratio of the leading coefficients, and I'll show you what I mean by that in just a moment with the examples up here. When the degree of the numerator is bigger than the degree of the denominator, then we have what's called an oblique or a slant asymptote. And we're going to have to do some long division when we do that. So let me go back to these examples up here. So here we have the same, the degree up top is 2, the degree down below is 3. So we have this scenario where the degree of the numerator is less than the degree of the denominator, so the horizontal asymptote is at y equals 0. Here the degree is the same. They're both 2. And when they're equal, the ratio of the leading coefficients becomes the horizontal asymptote. So in this case, the horizontal asymptote, the leading coefficients are 5 and 7. So what's going to happen is the horizontal asymptote is going to be at y equals 5/7. And there's some graphs later that we'll be doing where we'll see exactly what that looks like. Here the degree is larger. And so what we do is we do some long division. We do some long division here. And we end up that we have what's called a slant asymptote. And that's going to mean that instead of a vertical asymptote or a horizontal asymptote, we're going to have a slant one. And so the graph's going to get closer and closer to that slant. Let me show you what I mean by that. So we're going to find a horizontal or slant asymptote as we're looking at this. The degree is the same. So the horizontal asymptote is exactly y equals 4/7. So it's, again, the lead coefficients. Here the degree is smaller than the degree in the denominator. So automatically the horizontal asymptote is y equals 0. So again, this is so far horizontal asymptotes. Horizontal asymptote. Here, however, the degree on top is bigger than the degree down below, and so we can do some quick division, in this case synthetic division, and we end up with basically a straight line as the asymptote. So you can see as x gets larger and larger and larger, that gets closer and closer to 0, so we just end up with that there. Graphing rational functions. This is huge and can be quite complicated. These are the main things that we're going to be looking for. First of all, is there a y-intercept? There nearly always is. The only time that we're not going to get that is when we have a vertical asymptote at 0. And so when you set x equal to 0, you get y equals some number. So that's how you find the y-intercept. That's with any graph. Are there any holes? Again, we talked about that before. Factor and then cancel anything out. But what you cancel is where the hole is going to be. X-intercepts, you set y equal to 0. That can get a little complicated. And later in this chapter, we'll talk about when it does get complicated, what do you do? Vertical asymptotes, you set the denominator equal to 0. This is after you've already identified the holes, because here you also set the denominator equal to 0. But as long as nothing cancels out, or after they do cancel out, what's left in the denominator, set it equal to 0, and x equals whatever number that is that makes the denominator 0. That's your vertical asymptote. Horizontal and slant asymptote, just on the previous page you saw there are 3 cases. When the degree of the numerator and denominator, one is bigger than the other or the same. Those are those 3 cases. We just talked about that. And then the sign of the graph. That's going to be that lead coefficient, exactly what's happening with that. So those are the 6 main things that we're going to be looking for with that. And we're going to take some baby steps here and talk about what the domain is of each of these. Well, in this case, for sure, x can't equal -2. When you plug a -2 there, you get a 0 in the denominator, and that's bad. And actually, when x equals -2, we're going to have, again, our vertical asymptote. Vertical asymptote up here. That's out of screen. Vertical asymptote right there. Here, do you see that the denominator will never equal 0? Whatever you put in there, after you square it, you end up with a positive anyway, and then you add 1 to that. So there are no limitations at all in this domain. Once again, writing this in interval notation, you would go from -infinity to -2, parenthesis, because we're not including -2, or, which is the union symbol, parenthesis, because again, we're not including -2, off to infinity. This is basically -infinity to positive infinity, but we're skipping -2. Part C, we factor it, set each piece equal to 0, and we can see at +5 and at -1, we're going to end up with a 0. As we do that. And none of those reduce out with the numerator, so at -1 and at -5, we are still skipping over -1 to 5 and skipping over 5. And by the way, even if we could reduce those out, we would still skip them like this. It would still look the same. All right, and again, we're not quite to graphing them yet. That'll be the one of the sections coming up. So if we were to graph this, what we would end up with is using the transformations, yeah. So you can see in the x direction, it's the same as 1 over x squared. It's just shifted over. So, and then you're going to multiply y by 2. So here's the right 2. That's what that means. It's opposite. So negative is always this way, but when we're doing a transformation like this, we actually move in the opposite direction. And there's some reasons for that. This also is going to shift the whole thing up. That's the +1 here. Next up, here we have a function. We're going to go through all these various pieces. First off, I'm going to notice that the numerator degree is larger than the denominator, so we're going to have an oblique or a slant asymptote. The domain, I went ahead and factored, and you can see in the domain, for sure, x can't be -5. We definitely have a problem at -5, and so it's everything but -infinity to positive infinity except -5. The y-intercept, once again, is when x equals 0, and can you see when x equals 0, we get 6 over 5, and that's where that comes from. The x-intercept is basically where's the numerator equal to 0, and you can see when x equals 2, we get 0, and when x equals 3, we get 0. So there's our 2 zeros, or x-intercepts, as we're looking at that. Are there any holes? Well, no, not in this case. Nothing reduces out. If it did, then we would have a hole. She wrote in D and E. That's what you're supposed to put that does not exist into my open math. Vertical asymptotes at -5, we're definitely going to have them. It's not in the domain. And at x equals -5, we definitely have a vertical asymptote. Again, had it reduced out with another x plus 5 up here, then it would be a hole. Horizontal asymptote. There is no horizontal asymptote because the degree on top is bigger than the bottom because there is an oblique asymptote. And you can see she wrote this out very nicely. by doing long division using synthetic division. And you can see once again as x is getting larger and larger and larger and larger, what takes over, that goes to 0. What takes over is the line y equals x minus 10. Well, I hope that